Continuing along with the same notion of Ka and Kb and what it all means, all right? So if we go to our generic weak acid equilibria reaction, and here I've got it written as HA, the acid, plus H2O, the base, makes H3O plus, conjugate acid of HA, and A minus, the conjugate acid of the base, that's why I drew these blue and blue, and then the acid makes the conjugate base. Okay, so I could also write this in the shorthand way, HA, by omitting water, right? And that just becomes H plus and A minus. So now the amount that any acid will dissociate is dependent upon two things: its initial concentration and Ka value. Okay. And when we think about what this percent dissociation is, it's going to be the same way we calculate the 5% rule that we introduced in equilibrium. So in other words, the percent dissociation is the amount dissociated over the initial concentration, and of course times 100 to bring it up to a percentage. So then how do you do this from an ice table? Well, if we think about it here really quick, ice, rice table, I forgot the R. So we'll do our generic reaction here for just HA, H plus, A minus, okay? So let's suppose we have some initial concentration of HA, and I'll note that that is HA sub 0. So we'll just say whatever that number is, that's our initial concentration. Okay, so, and then of course, initially we'll say that's 0 and 0. We're going to see this pattern a lot. We start with some initial amount of reactant and we have 0 amount of product. So now we know the change of this is got to be minus X, and this has got to be plus X and plus X. And so that means, of course, at equilibrium, this is the initial HA concentration minus X. This is just X and this is X. And so the way that we calculate the percent dissociation of a weak acid is just simply taking that value of X, which is the amount dissociated, divided by our initial HA concentration, and of course times 100 to bring it up to a percent. So the same way we did it before. So now what does all of this mean, and how does that impact the 5% rule? Well, here's calculations of percent ionization versus concentration for HNO2. Okay, so the HNO2 is a weak acid, right? And it is in equilibrium with H plus and NO2 minus, okay, aqueous. And so now this has a constant Ka value, all right? And we remember here that this percent ionization, this y-axis, is calculated from, X, the amount dissociated, divided by the initial, I'll replace that with HA, and I'll just write the initial HNO2 concentration, and of course times 100 to bring that up into a percentage. And what you can see here, as you get more and more concentrated, the percent dissociation really drops, okay? So the degree of dissociation or ionization for a weak acid decreases with increasing acid concentration, right? So you can see if we had something like, let's suppose this was 0.01 molar, which I think is a good guesstimate based on this graph, okay? So you can see the percent ionization for nitric, this is specifically for nitrous acid, sorry. At 0.01 molar, its dissociation is something like 17%. So at that concentration, we could not use the 5% rule, okay? But now notice when the initial concentration becomes 0.1, it's dropped to something like, 8 or 9% or something like that. And as you can see, if we were to go out to larger and larger concentrations, we would eventually hit that 5% rule and then go under the 5% rule, okay? So how does this impact the 5% rule? Well, the more concentrated our initial weak acid is, the more likely it's going to pass the 5% rule, okay? And so also that means the more concentrated our acid is, the less it dissociates, which is kind of interesting.